everyone, in this video we're going to talk about biofuels, limiting reactants, and gas laws. So we're going to start topic 5. Alright, so this is one of my favorite topics to talk about, biofuels. I'm going to try to keep it brief and not drone on. But in order to talk about biofuels, I think we first need to talk about regular fuels. So we need to understand what these are chemically. So think about what kind of fuel sources that you use at home or while you're out and about. I've given you a little bit of a hint here. Here's one fuel source that you're probably used to seeing. So what are some things that you regularly interact with? What types of fuels do you use? So some of the things that you might have come up with are gasoline, stuff to put in your car. We have, let's see, propane. This is propane. We have butane, actually, in lighters, if you've ever seen that before. Sometimes you all have natural gas to heat your house. This is also a fuel source. So these are chemical fuel sources. Now, electricity is usually coming from a chemical fuel source, but that direct electricity into your house is not quite a fuel source. So we're going to talk about all these different places where we get energy from in order to pretty much fuel everything that we do. Okay, so these are all chemicals, and most of the energy that we use comes from chemical reactions. So we're going to examine that. So let's take a look at how some of our fossil fuels are made. These are common chemicals that we use to create energy. This is one of them. This is a fossil fuel here. So fossil fuels come about by the decomposition of carbon material. So things break down in the earth, and all of these carbon molecules are compacting and compacting. Chemicals are breaking down until they become their simplest forms, which is hydrocarbons. This is what we call a hydrocarbon. It's just hydrogen and carbons. So things like bacteria and fungus break down molecules into simpler ones. And pressure with heat and time turn them into things like hydrocarbon, which we use as fuels. So here's a common fuel that we actually use, methane. So this is our natural gas, is methane. This is the chemical structure for methane. It's a carbon with 4 hydrogens attached. Let's take a look at some other fuel sources that we commonly use. Coal is one that we use to generate electricity in power plants a lot of times. This is the chemical formula for coal. You can see it's got a lot of carbons, a lot of hydrogens, some oxygens, and some nitrogen, and even sulfur sometimes. We have things like petroleum, which gives more energy than coal, and it's just a mixture of hydrocarbons, so it's got more carbons and hydrogens in it. Gasoline is a more specific type of hydrocarbon. So gasoline is a mixture of these that only contain 5 to 12 carbons. So petroleum is all kinds. It can be a mixture of all of these, but gasoline in particular only has 5 to 12 carbons. It won't have 4 carbons or 13 carbons. It's gonna have that specific range. Propane, this one has 3 carbons in it. That's specific to what that is. If you've ever had, like I said, butane lighters, this one has 4 carbons in it. So these are all hydrocarbons. And then methane has 1 carbon in it. You can see its structure up here. This is our methane. And then ethanol is another one that we use a lot. So ethanol contains oxygen in it. It's got 2 carbons. And it has 1 oxygen. And so it's not technically a hydrocarbon because of that oxygen in there, but we do use it as a fuel source, and we're going to talk a little bit more about it as we go on this chapter. So where do we get these fuels from? We get these fuels from deep in the earth. That's where our fossil fuels are coming from. Here's an overview of how we get a lot of our fossil fuels. So this in particular is where we get methane from. So this is your natural gas. So natural gas tends to come from deposits in the earth. So inside of the earth, we have these like gas-rich pockets here. And we use these drills to get down in here in order to put pipelines in so that we can extract these materials from the earth, and then that goes to your house. So that's where we get our methane sources from. We also get other fossil fuels in this manner. We drill them from deep in the earth. Now, that being said, that doesn't mean there's methane in other locations. So methane actually is there can be biogenic production of methane, so it comes from other places besides just deep in the earth. There are actually bacteria that make methane. So this is where all these different bacteria are located. This is really cool. Microbiology is also super cool if you happen to get into it. There are bacteria that live in rice paddies that create methane. There are things deep in the ocean that actually create methane. There are bacteria that live in these hydrothermal vents that come from deep in the earth, and they like the warmth and they actually live there, and they produce methane. We also have some from our landfills. There are bacteria that live there. Wetwood trees, cows, and horses. You probably hear a lot about this methane coming from like cow farts, right? So there are actually bacteria that live in these animal stomachs, and they produce methane. So we also produce some. And here's another deep sea vent, termites, and other types of protozoa. So there are different types of methane that can be produced. There are some that come from deep in the earth, that's like a fossil fuel, and then we have biogenic methane, which comes from biological sources like bacteria. I wanted to talk a little bit about methane emissions from landfills, just so you get an idea of the scale of this production. So municipal solid waste from your landfills is actually the third largest source of human-related methane emissions in the United States. So there's a lot of methane gas coming off of your landfills. So this is your trash here, and it's breaking down in the landfill, and it produces this gas. And sometimes this gas can be captured, and it can be used to generate electricity. So let's see here. Okay, so in 2016, 14.1% of our methane emissions were coming from landfills, which is a pretty big number. Unfortunately, right now, we aren't using as much of this methane as we should to produce electricity, just because the technology isn't quite where it is. Just to give you an idea of the mixture of gases that are coming off the landfills, we have about 50% of the gas is methane, and then the other 50% is carbon dioxide. So this is important because these are both greenhouse gases. And our methane, again, is a natural gas. We can directly use that to power our homes. So it's kind of wasted if we just let it go out into the atmosphere and don't use it for something. That is changing, which is good news. I think 2021 has been a great year for renewable energy because of the pandemic, actually. There's a lot more investment going into renewable energy sources. But looking back at 2019, there was actually a lot of unused methane from landfills. So if you want to learn more about that, you can check out this website here and read a little bit more. I think it's really fascinating, and I'm hoping to see more work done on it in the future. Okay, so let's look at the chemical composition of some of our fuels. So our methane was our carbon with our hydrogens. It has 1 carbon and 4 hydrogens stuck to it. Butane has 4 carbons, so it's going to be carbon, 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 carbon. Instead of drawing all the hydrogens, I'm just going to put a little dash here. These represent hydrogens, okay? Our propane has 3 carbons. It's going to have 1, 2, 3, and it's going to have hydrogens all over here. Okay. Our octane, octa, this means 8. Buta is 4, prop is 3, octane means 8. So this is going to have 8 carbons in it. This is what our gasoline mostly contains. That's why you see an octane rating on the gas that you purchase. 1, 2, 3, 4, 5, 6, 7, 8. So octane, even though it looks big here, is actually it's not too big of a hydrocarbon, because remember that I said that your gasoline that you buy at the pump is somewhere between 5 and 12 hydrocarbons. So octane is what's ideal for your engine in your vehicle, but there is a mixture of other stuff. Now ethanol, let's take a look at our ethanol. This is another fuel source we commonly use. It's got 2 carbons in it, and it's got some hydrogens here, and then an oxygen and another hydrogen. And that's the structure of your ethanol fuel. And these are things that we commonly use for energy. So in order to create energy from these hydrocarbons, what we do is we break them down. So they get burnt, right? They're combusted. So we'll have our CH4, like our methane. We add oxygen to it, and it turns to CO2 plus H2O. And this produces energy, right? It gets hot. So essentially what we do to power our homes, to power our vehicles, is we burn fossil fuels. That's how we get all of this energy to do all the things that we're doing. We burn these chemicals right here in order to create energy. Let's take a look at oxygenation of fuels. So I wanted to highlight here a couple of things. I wanted to look at the difference between your ethanol, OH, these are little hydrogens. Remember the dashes are hydrogens, I'm just not drawing them in, versus regular hydrocarbons. So let's say here, let's look at this molecule versus this one. So I want to look at the effect of oxygenation on the energy of a molecule. And so if we look here, each of our chemical bonds has an energy associated with it. So a carbon bonded to a hydrogen contains a certain amount of energy. It has this 413 kilojoules per mole. That's a unit of energy. A carbon-to-carbon bond has this much energy contained in it. So what that means is if we break it, that's how much energy is released. Now, if we look at our carbon-oxygen bond, this is how much energy it contains. Now, you'll notice a big difference here between our carbon and hydrogen and our carbon and oxygen. Our carbon and hydrogen has more energy in it. It's 413 kilojoules per mole for our hydrogen versus our carbon to oxygen, which is only 358 kilojoules per mole. So it doesn't have as much energy in it. And what that means is when we burn these fuels, they give off less energy. So this affects how much we can get out of these fuels. So this one would contain less energy than its counterpart because it has less carbon-hydrogen bonds in it. So let's look here. Okay, so that's one thing that affects your fuel source, is carbon-oxygen bonds have less energy than our carbon-hydrogen. They have more energy. Another thing is just having more of the carbon-hydrogen bonds is going to give you more energy in general. So let's look at 2 different chemical structures. This is what we call a double bond here. And when we have a double bond, it means we have less hydrogens. We're going to learn this later in the class, why this happens. Here's the other structure. So when we have a single bond in between here, let me highlight our bonds. Okay, so this is our single bond, this is our double bond. We have more hydrogens when we use single bonds. So you'll see we have 6 hydrogens here, and we have 4 hydrogens here. So what that means is we have less carbon-hydrogen bonds to break, meaning there's less energy. So less energy to be had. And there's more energy because there's more carbon-hydrogen bonds. So what that means for us is when we're looking at a molecular structure of something, we're looking at the compound. In order to have a lot of energy, what we want is we want a high hydrogen to carbon ratio. We want a lot of these hydrogens in order to have that. When I say saturation and unsaturation, unsaturation just means double and triple bonds, double and triple bonds. And something that is saturated has only single bonds. So you may want to write that down. only single bonds. So if you hear those terms, you don't get confused. So what that means is if you have a saturated compound that's only single bonds with a lot of carbons and hydrogens, that's going to have more energy than something that's got double or triple bonds in it, because that's going to reduce the amount of hydrogens that you have attached to your molecule. So we're looking for this high hydrogen per carbon ratio. The other thing that's going to make our fuel sources high in energy is having bigger molecules. So in general, if you have more carbons to stick hydrogens to, you're going to have a lot more energy than if you have less, like this. So there will just be more hydrogens in general on a molecule that has a longer carbon chain versus this one, because there's just more space to fit them in. Okay, yeah, more bonds in general. There we go. And if there's more bonds, that means you can break more bonds and you can get more energy from them. So in summary, here's kind of what we learned from the last slide. What we learned is that fuels with more oxygen, have less energy. So CO versus CH, less energy for these. Lower hydrogen to carbon ratios have less energy. So more hydrogens per carbon equals more energy. So if you have less hydrogens per carbon, less energy. If you have a shorter carbon chain, there's less energy. So the bigger the molecule, the more CH bonds, the more energy there is. So more bonds, i.e. a bigger molecule, equals more energy. Make sure you have this written down because the quiz is going to ask you about this on the next slide. So if you need to pause, go ahead and pause and make sure that you have this summary written down and you understand these three principles. Let's take a look at the question now. So I'm going to ask you to list these molecules in order of containing the most energy to the least using what we just learned about our hydrogen to carbon ratio, the size of our molecules, size, and oxygenation. Okay, so make sure that you use these three rules that we learned here in order to list these molecules in order containing the most energy to the least. So you're going to look at this one versus this one versus this one versus this one here and see which one is going to have the most energy. Let's take a look at how to solve this problem. So first things first, let's look at how big our carbon chains are. We've got C2, C6, C8, and C6. So if we wanted to place these by size, this one's going to be the smallest. This one's going to be the largest. And the C6s are going to be about the same size. So on our smaller size here, that usually means we have the least energy. So I'm going to go ahead and place that one as least. We're doing this from greatest to least. Hold on. So we'll put this one as least, and we'll verify that. And we're going to put this other one as most, C8H18. So most energy, least. And then we'll need to look at the other two in the center because they've got C6s. Okay. We can also verify that this one's pretty low because it's got an oxygen in it. So it's in general going to have less energy. There's no oxygen here. So that's a good sign that it's going to be high energy. Okay, let's take a look at our carbon hydrogens. So we've got CH18 versus CH12O6. We can already see that this one has a lot of oxygens in it, meaning it's going to have less energy. So that one will be on the lower end. And then the C6H14, oh sorry, I circled the wrong one, C6H14 is going to be on the higher end. Same reason. There's no oxygens, so it's going to be higher energy. And when you have no oxygens, that means you're going to have a higher hydrogen to carbon ratio. So for every one carbon, we have more hydrogens per that carbon, because those spots on the carbon, there are 4 locations in which something can be, are not taken up by oxygen. So they're fully filled with hydrogens, versus something where you have an oxygen, one of these spots might be occupied by an oxygen. Therefore, you have less hydrogens on that carbon. Okay, so this is how we would order these. Most of these on the exams and your homeworks are going to be pretty intuitive. I will space things out so that you can clearly tell which one is going to have the most or least. There shouldn't be too much gray area on these. If you have any questions, let me know.